Hi, welcome back to this topic on AI HPC infrastructure. So continuing on this topic, we'll be talking more about containerization. So this topic is on containerization. Now to understand containerization and what it is, we need to first examine what is called virtual machines. Now virtualization is actually important for machine learning. Knowing how to host machine learning applications, for example, the training or testing pipelines, is an essential skill for a machine learning engineer. And deploying machine learning models have a variety of possibilities. Reproducible machine learning environments were a challenging problem to solve a few years ago. The problem of it works on my computer but does not work on another teammate's computer causes many wasted hours of debugging the configuration differences between the two machines rather than trying to solve the machine learning problem itself. So having a reproducible development environment that you can easily port over from machine to machine and having it being able to work in a consistent manner saves endless hours of this wasted effort in just debugging configuration differences. Now, this kind of problems have been addressed using what we call virtualization technology. Virtualization technology has been used for machine learning workflows to overcome these problems. Fast resource scaling, transitioning deployment environments between cloud providers, and even moving applications from on-premise to cloud is easier to accomplish with virtualization. So for the data scientists and AI scientists, virtualization hides the underlying complexity of the hardware and software in the AI HPC infrastructure. Let's continue to take a look at what is the kind of complexity that we may encounter in the AI HPC infrastructure by taking a look at the infrastructure for the National Supercomputer Center. This slide shows the structure of the National Supercomputing Center. So in the core, we have the Aspire Supercomputer 2A, where the HPC resources are made available on the hardware, and we have the administrators. And you can see that we have what we call the container host that actually house these virtualized resources called containers, which we'll talk a little bit later on. And then you can see that there's also large storage resources, for example, this data lake actually to store data for the machine learning experiments and other experiments that there may be. And there's also what we call the batch running software, such as some of this workload management capability. And then there is this Jupyter servers that we can use in the digital sandbox. And there are also additional data fabric or data resources that may be in the various agencies and government bodies making use of the shared resources. So you can see that actually the underlying structure is quite complex. And if we were to try to use this and we need to actually control each and every one of these servers, for example, Jupyter server, GraphQL server, and start the Jupyter kernel running, and if we want to access a certain part of the data lake, we need to also configure it manually ourselves. It may be too much work for most data scientists who are just interested in getting the right data and solving their problem rather than to mess around with the complex infrastructure here. So the idea is to hide or keep away the complexity from the data scientists and AI scientists so that the scientists can focus on the data problem itself than struggling with the infrastructure. So in this set of slides, we're going to talk a little bit about the different levels of virtualization. Now, virtualization is basically a process of running different virtual instances of a computer system. So you can think of it as a software computer. So it's many multiple versions of this software computer running on a hardware computer itself. So we have multiple virtual computers rather than just one single computer running the software on the bare metal itself. So what makes this possible is something called the virtualization layer. So beneath the virtualization layer, you have the normal underlying hardware, and on top of the hardware, you have the operating system like your Windows or your Linux or your Mac OS that controls the underlying hardware. Now, typically, the host operating system is intended to control or organize the resources for one physical computer, right? It's not meant to create multiple instances of itself and run multiple different operating systems. So the host operating system just gives you one physical computer. Now, the problem is that if you do this, the resources on this computer, especially for large computers like a supercomputer, may not be efficiently used by that one single operating system itself. So in order to fully use the hardware, what is commonly done these days is to actually introduce a virtualization layer, this one over here, that rides over the host operating system. And what the virtualization does is that actually provides multiple virtual copies of the underlying hardware. So we can now run multiple different virtual PCs or virtual instances on top of the virtualization layer, and each of these virtual PCs or virtual instances, or also called virtual machines, will have their own software version of the hardware resources. So for example, a certain amount of storage or hard disk, we can actually create a virtual hard disk to be attached to this particular virtual machine, and another virtual hard disk to be attached to this machine. The underlying RAM that's available, or random access memory that's available in the underlying hardware, the physical RAM itself, is going to be partitioned and divided into virtual RAM locations for each of these virtual PCs. So this is really literally running multiple copies of a software PC on top of a physical PC or physical machine or server itself. So we have multiple machines, virtual machines running on top of one single hardware. But because each of these virtual machines have their own software applications, their own operating systems, and they use a certain percentage of the underlying physical CPU, in combination, they fully utilize the underlying hardware capability. Because each of these jobs may take a certain percentage, but add up together, they make full use or close to 100% of the underlying CPU resource itself. The virtual instance runs in layer abstracted from the actual hardware. So it actually creates a virtual hardware over the actual hardware itself. To the applications that's running in each of these virtual machines, the applications, they are not aware they're running within the virtual machine. They just they appear, as far as the application is concerned, it seems to have total control over its own virtual hardware. Right, so it's actually, it will appear to them, this application, as though they are running on their own dedicated machine, albeit it's the software emulation or something like that. When it comes to virtualization, there are actually two main methods of doing this. One called virtual machines, and the other one called containers. Now virtual machines and containers, they are the most common ways of deploying applications inside a virtualized environment that's isolated from the underlying hardware. Now, the main difference between containers and virtualization really is the level of abstraction, or the level to which we actually hide the underlying hardware from the application itself. So the level of isolation is much more for virtual machines, but because of the additional level of isolation, we also have additional complexity, and more of the hardware resources are actually going to be used up just to support this isolation rather than doing actual useful work. But because it is actually going to be almost completely different virtual machines running inside these virtualized instances, we can even run different operating systems over the underlying hardware. So the underlying hardware may have a Linux operating system running on it, and because of the virtualization layer within each of the virtual machines, we may actually be running one virtual machine running Windows, another virtual machine running maybe Mac OS, or yet another virtual machine maybe running Linux or Windows Server OS. So the level isolation is complete enough for you to actually run different operating systems in each of these virtual instances. And depending on the application requirement, we can have free play, right? We can choose between different types of VMs or containers, depending on how much isolation we actually need to run the application. So it depends on the application requirement. So if you need more isolation and you need to run on a specific type of operating system in order for the software to work, then there's very little choice. You probably need to use a full virtual machine. But if you don't need that level of isolation, then the more lightweight solution, which is containers, and we're going to talk a little bit more about containers later, will probably be able to solve the problem for you. The containers are much more lightweight version of these virtualized instances. So in this set of slides, we're going to talk about the virtual machine architecture as well as the different levels of virtualization. So virtual machines are virtualized services hosted on the physical machine itself with its own operating system and on the physical machine. And what we are creating are virtual machines that can host different kinds of software. It offers the flexibility that you can host actually the applications without concern about managing the physical server itself. This is actually done by the server administrator, by the physical server administrator. The virtualization layer is also called another alternate name for it is a hypervisor. It's like a supervisor program, but it provides multiple virtual instances of the underlying machine, and in each of these software-driven virtual machines, we can have our own operating system. This operating system could be similar to the operating system for the hardware itself, in the sense that this could be also maybe a Linux operating system, and the original hardware is also running off Linux. But the guest OS can also be running on a different operating system, for example, Windows, or a different version of Linux from the hardware's operating system. And the application suite as well as the libraries in each of these virtual machines could be completely different. Now, each of these virtual machines are actually not aware or completely isolated from each of the other virtual machines. They're actually not aware that they are actually physically sitting on the same machine, because as far as the applications and OS are concerned, they have their own dedicated virtual server. They are not actually able to see the other machines within the memory or the hard disk space of this single virtual machine. So they are completely isolated from each other. But of course, physically, the resources that are running on this machine are basically derived from the underlying hardware. So for example, the hard disk that's actually in the underlying infrastructure is actually being shared across each of the virtual machines. So at the hardware level, the main operating system should be able to see the space that's being occupied by each of these virtual machines, and would be somewhat aware of how these machines are actually operating over the hardware. However, the hypervisor actually contains more of the information that makes this sharing possible. So the underlying operating system has some notion, but doesn't have the full complete information that's only going to be present in the hypervisor itself. So the main concern of the underlying operating system is just to share the hardware resources to the hypervisor layer, and then the hypervisor layer is the one that's actually responsible for sharing out those resources to the individual virtual machines. And in each virtual machine, it actually doesn't know that it's sharing with anybody else. It just looks like it is a dedicated virtual machine or virtual PC running within the hardware itself. And it is not aware of the other two virtual machines or other virtual machines running on the same hardware. So what are some of the advantages of virtual machines? So everything running inside the virtual machine is on the guest operating system, and this is actually independent of the host or the underlying physical OS that I was mentioning just now, and also the hypervisor. So to start a VM, a hypervisor starts a process to manage the virtualization process for a specific virtual machine, and the host machine operating system and the host hardware then allocate some of those hardware resources for that particular virtual machine to use. The hypervisor bootstraps the dedicated kernel environment and also a large set of operating system processes at start time. This makes the size of the virtual machine much larger than containers, which only contains a specific application. So this is why I say that containers are actually a more lightweight version of virtual machine. Virtual machines, they have to duplicate all the hardware, all the virtual hardware as well as all the operating system resources required, and the guest operating system can be completely different from the host operating system. Now, running a dedicated kernel and OS has three main advantages. This is the advantages of a virtual machine. Number one, security. So it's completely isolated from the other virtual machines. So there's no way of knowing what's running inside the virtual machine from the host machine, because the host machine is not actually aware of what's it. Only a hypervisor knows what's running within it. Secondly, portability. So it's possible for you to just save the entire virtual machine into an image and then run this entire virtual machine on another physical machine, and it's basically a cloning process. It's completely, we will just clone the whole operating system, including the hard disk configuration, the library configuration, the application configuration, everything running within the virtual machine, and then you can actually port it over to run on another server. Yeah, so it's actually possible to run the hypervisor on every virtual operating system, including Mac, including Windows, and including Linux, and different types of operating system in the virtual machine. So it's a very portable way of doing things. And thirdly, you can use this as a backup mechanism. So you know that you have one image or whatever you have within the virtual machine running very well, and it's actually your production software. If there's something that actually fails at a later point in time, you can always go back and take the backup image of the entire virtual machine, and then you instantly be able to run it again from that snapshot or the backup of the virtual machine. So it is a very good way to actually be able to have instant restoration of a service without having to reconfigure the machine all over again, because it is actually every virtual machine is a mini server, right? It's actually a virtual server complete with operating system, with hardware resources, etc. Just that it is running within an environment that is actually created by sharing from the original hardware itself. So what are some of the disadvantages of virtual machines? So, however, virtual machines, they have they have major limitation in hosting modern applications. So every virtual machine is backed by a copy of the entire operating system with all the application libraries, etc. So the virtual machine image is actually going to be quite large, because not only does it have the application software, but it also has the OS or the guest OS of as well, and a modern OS like Windows or even many versions of Linux, they do take up quite a bit of this space. So all this has to be there besides the actual running application code. And since virtual machines images can become quite large, in order to, and they have a size in the order of tens of gigabytes, including the bootstrapping, updating, etc. Migrating these large images is going to be difficult to pull off on without high dynamo, because it just takes a large amount of time just to copy the images from one place to another itself, because of the sheer size of the images. And maintaining multiple large images, because you want to have multiple versions being backed up at different times, becomes a lot more unwieldy. And there's also issues with sharing the virtual machine with GPU acceleration, which we're going to see why this is going to be a problem, because graphics processor units or GPU, they are increasingly very critical in accelerating the AI processing or the machine learning processing, in the sense that without the GPU acceleration, many of the algorithms such as deep learning will take simply too long to do the training to build a model. So we need to make sure that our virtual machines are also able to share the GPU resource to multiple virtual machines without them interfering with each other. And this remains to be a challenge. Okay, sharing the GPU hardware using virtualization is still a bit tricky. Uh, there's some sharing that actually allows, for example, the 3D API calls, for example, OpenGL and DirectX, which is just for the graphics capability. But these 3D API calls, they are not optimized to share out the kind of API calls that we need for accelerating machine learning. So things that are specific to things like the NVIDIA CUDA libraries, most of the existing hypervisors don't really share this kind of mechanisms out to the virtual machines yet. So one mechanism that's also been used to allow this to happen is what we call the hypervisor pass-through, which basically is like a shortcut. It allows the GPU resource to be shared with one of the guest OS. It's not really shared, it's just that there's a shortcut from one of the virtual machine directly to the underlying hardware. So it's not a sharing mechanism, there's a shortcut that basically allows one of the guest OS, guest VM to take over the resources on the virtual machine. Sorry, on the graphics processor unit or GPU. Okay, yeah. However, this does not mean that we are sharing. It's just that at least one of the virtual machines can do accelerated training for machine learning, but the others are just going to be using the CPU resources without the GPU. So there are actually some tools to automate the creation of virtual machines, especially virtual machines that we want to use for machine learning. So one of these tools is something called Vagrant. So Vagrant is a tool that helps to manage such virtual environments. It is a means to work with virtual machines as well. It provides a simple and easy command line interface for the client to create and manage the images, and as well as it also contains an interpreter for text-based definitions of what the environment should be like. And these text-based descriptions or definitions are what we call Vagrant files. So Vagrant is the open source, which means that anyone can download, modify it, and also share it freely. Out of the box, actually Vagrant supports some of the key hypervisors like VirtualBox, or virtual machine hypervisors like VirtualBox, VMware, both the Fusion and Workstation version, as well as Hyper-V, which is actually the Windows version of the hypervisor. What this means is that Vagrant can automatically create VMs, and you can reproduce this time and time again if you store the Vagrant file. Right? Once you have defined the Vagrant file, you can just spin up multiple versions of the virtual machine by just running the Vagrant file over and over again. And the Vagrant file will always be able to reproduce the same environment for you, no matter how many instances you want. Right, so this also gives you the additional reproducibility. So once the Vagrant file is working to create one copy of the virtual environment that you want, and you need additional copies, just spin up from the Vagrant file additional copies of the VM that you need. Right, so using this, you can automatically create the VMs of your environment as needed, and then apply the configuration and run it. And with that, we actually come to the end. So there are other commercial tools for controlling machine learning, but Vagrant is the popular tool and it's actually available as open source as well. So thank you for your attention, and I'll see you in the next set of slides.